We are going to do a couple word problems today, but we're going to start with our dot product and our angle between vectors. And the dot product is how we multiply vectors. And it's a little bit different than what you would think, but suppose we have vector u, and that's equal to a, b, and then vector v is equal to c, d. When you multiply two vectors, so we learned how to add and subtract them the other day, and that was no big deal. But when we do u times v, what we get is you take a times c, so you multiply the two horizontal components, and then you add b times d. So you multiply the two vertical components. And so you get a numerical result. So one vector times another vector does not result in another vector. It simply results in a number. Okay? So let's try this first example. We have u times v. Oh, I'm gonna change this every year. I say I'm gonna change this. I never do, but people get confused by it. Okay? So we're gonna make this vector negative 1, 5. Okay? So u times v, I just do what times what? Negative 1 times 2 plus 3 times 5. Good. And so you get negative 2 plus 15 is 13. So the dot product is 13. Yes. Yeah. Sometimes things are difficult. Told you it was going to get easier. All right. In order to determine the angle between two vectors, we say that, and when I say two angles, suppose you had vector u, and suppose you had vector v, and you wanted to find this angle theta that sits between them. The way that we do that is we set up an equation. The equation is cosine of theta is equal to u times v, so the dot product, divided by the two magnitudes multiplied together. So finding the magnitude and direction of a vector is something that we focused on last Friday. You may not remember it, I understand. But today what we want to do is we want to find the dot product of vectors, and we also want to find the angle that exists between the two vectors. So we have the dot product right here. Everybody see that? Okay, so now I'm going to find the angle, so I'm going to set up this. Cosine of theta is equal to, and I just use this formula. On the top goes the dot product. Have we done the dot product already? Very good. 13 divided by, and on the bottom we have the magnitude of u and the magnitude of v. So let's look at the magnitude of u. What is the magnitude of negative 1, 5? I do the square root of a squared plus b squared. Anybody see it? Square root of 26. And then I have to do the magnitude of v. What is going to be the magnitude of v? Square root of 13. All good there? So I just have to put this in a way that I can type it in my calculator. I am going to take the square root of 26 times, I'm going to take 26 times 13 just so I can see. I get 338, so I get 13 over the root of 338. All right? So cosine of theta is equal to that. Suppose I want to find the angle. What do I do in order to find the angle? Cosine inverse. Good. So we're going to cosine inverse, and I'm going to type in 13 divided by the root of 338. And I'm going to make sure I'm working in degrees, which I am. Vectors are in degrees, and I get 45 degrees. We all okay with that? So you press mode, and in mode you have degrees and radians. Okay, let's try this one together. Notice that this is written in terms of I and j. So this would just be 1, -1, and then this would be 3, 4. So I want to find the dot product, and I would like to find the angle between them. So A times B, vector A times vector B. How do I calculate that? Yep, 1 times 3 plus -1 times 4, and I get 3 minus 4 is -1. -1 is the dot product. Everybody okay with that? All right, so then we set up for the angle. Cosine of theta is equal to what goes on the top? -1, the dot product, divided by the magnitude of A times the magnitude of B. What is the magnitude of A? The square root of 2. And then what's the magnitude of B? Which is 5, right? See that? Okay. The magnitude is going to be the square root of 3 squared plus 4 squared. And so we get the square root of 9 plus 16, or the square root of 25, which is 5. So just be careful as you type this into your calculator. I'm going to go cosine inverse, and this is where people make their mistakes on the test. I'm going to go -1. I'm going to divide that by parentheses 5 roots of 2. So notice how I'm just taking the square root of 2, but I'm dividing by both 5 and the root of 2. That's what you have to be careful about on your calculator. Press enter, I get 98.13 degrees. .13. It's going to be like Logan shot put today.
Oh, that would be awesome.
Yeah, he would set the state record. Okay, let's try again. 98.13. That's going to be like Tim's golf score today.
Oh!
Whoa, what's up? Yeah. See, I can play this game. Got Kendall to smile. Very good. All right. So you're going to have to do that on the test. Is it tough? But is it new? Yes. Orthogonal vectors are vectors that make 90 degrees. They're perpendicular. And here's what's interesting. If it's perpendicular, what is the angle formed? 90 degrees. What is the cosine of 90 degrees? It's 0. So this whole thing ends up to be 0. And so all we have to say is, in order to determine if vectors are orthogonal or perpendicular, it just turns out that their dot product is 0. If you get 0, you know that they're orthogonal. They're perpendicular. So let's just determine if these vectors are orthogonal. I take 2 times -1, and I add that to 1 times 2. What do you get? They are orthogonal. Yep. Maybe you remember the orthocenter from geometry. Had to do with 90-degree formations as well. This one, notice it's 5, -3, and then it's -6, 10. So I'm going to dot product that. I get 5 times -6 is -30, and I add to that -30. Does that make 0? No, it does not. It makes -60. So it is not orthogonal. Not too bad, huh? All right, so we're just kind of dipping into just the fundamentals of vectors, but the application of vectors is work. And we all love work, right? And from a scientific perspective, a physics perspective, mathematical perspective, we define work to be this. Work is equal to the amount of force that you apply on an object times the distance that you moved that object. And we say that that's the amount of work that's being done. So for example, if I push on this wall, am I applying force? Am I at some point going to get tired? I will feel like I worked out, correct? But have I moved it anywhere? So technically I haven't accomplished any work at all. Okay? So that's something to just keep in mind. So find the work done by the force by moving the object from P to Q. So the force is going to be a vector, and then the distance we're going to write as a vector as well. And so it says that we have a force of I plus J, or in other words, the force is equal to 1, 1. And then I have a distance. If I move an object from P to Q and it goes from 0, 0 to 3, 4, how far has it moved horizontally if it's moved from 0 to 3? 3. And if it's moved from 0 to 4, it's moved 4. So in order to calculate the work being done, all I need to do is to take this and multiply that. So work is equal to 1, 1 times 3, 4. And what do you get? 7. So you take 1 times 1 is 3, and you get 1 times 4 is 4. Add them together. That's our dot product rule. Let's try something just slightly different. I have a force of, so F is equal to 3, negative 2. And then I have a distance. If I move an object from P to Q, and it goes from 0, 3 to negative 1, 2, if it goes from 0 to negative 1, how far is it moved horizontally? Negative 1 units, right? You always take, so the negative sign doesn't matter. You always take the latter minus the former. So it's negative 1 minus 0, okay? So if you move from 3 to 2, how far is it going? Negative 1 as well. So we have 3, negative 2 times negative 1, negative 1. And how do I multiply that again? Negative 1 unit. That's not too bad, huh? Okay. Then we just have like 3 real quick little word problems to try, and that'll be it. Yeah. Yeah. So it's kind of time of the year. Anybody mow their lawn yet? I hope not. Okay, good. Who does, like, you were the lawn mower in your family? Okay, all right, very good. Isaac, are we riding lawnmower or are we push mower? Zero turn, wow. Same thing? Okay, all right, push mower? Okay, all right, okay. So in my family, my neighbor, he's like 87 years old. They're selling the house now, but he was kind of past that whole mowing the lawn point, so we would mow both yards. So we had a rider that we used for a little while, but I think this year's going to be a push mower, back to a push mower. All right, so we've got the lawnmower going again. Okay, so this picks up from a problem that we've worked on earlier. And it just says, you know, hey, we're pushing this lawnmower, and if we push at a distance of 80 feet, you know, and it's at an angle of 35 degrees to the ground, constant force of 60 pounds, like how much work have you done in that 80-foot pass? Okay? It'd be really cool if next time you mowed the lawn, you calculated this for your parents so you could give them a numerical representation of the amount of work that you did. Okay? So So let's do this. First, let's define a formula for work. What is the formula for work? Good. Force times distance. I'd like to do the easier part first. Let's calculate the distance. The distance we represent, and stop thinking about distance as just one term. Let's think about distance in a vector form. Okay? So what is the distance vector? What is the horizontal distance we push this along more? We pushed it 80 feet, so therefore that is my horizontal component. And then how far have we pushed the lawnmower up? Hasn't moved up at all. Yep. So that's my distance vector. Okay. Now let's figure out the force vector. And the force vector we can determine by this. It says a constant force of 60 pounds. That means that 60 is the force. It's the handle represented right there. And we have both a vertical component, I'll call that B, and a horizontal component, we'll call that A. Who remembers from Friday how I could determine the horizontal component of that vector? Yep. So you just take the magnitude and you multiply it by the cosine of the angle. So remember, cosine is horizontal, sine is vertical, cosine is x, sine is y. That will calculate the horizontal component. You may remember how I calculate the vertical component. 60 times the sine of 35. And so as we multiply that out, we'll see what we get, but that will tell me my vector in component form. So I have 60 cosine of 35. And I get 49.15. And then I have 60 times the sine of 35, and I get 34.41. So I have work is equal to the force vector times the distance vector. And the force vector is 49.15, 34.41. So notice as I multiply these together, what's going to happen? Which ones cancel? The vertical ones cancel. Does it make sense that there was no work performed vertically? Yeah, the object didn't move vertically at all. Although we have vertical force, it didn't move at all. So as we calculate this, we just simply take 49.15 and we multiply that by 80. And we get 3,932 plus 0, or 3,932. And then we need a label here. And what is our label in, what's our label in distance? Feet. So feet, but it's not per pound because we're not dividing by pounds. We're multiplying by pounds, right? So it's feet times pounds, foot pounds. And you've maybe seen some of these labels if you've, done any mechanical type work. Okay, that's not too bad, huh? Okay. What's that? Yeah, we're gonna draw another picture because it's fun. It's fun. Okay, so I got a car on a driveway, and the car weighs 3,200 pounds. And yep, that's my car. And it's on a 12-degree incline. And the question is what force is required to keep the car from rolling down the hill? Like, for example, could we put Drew right behind the car? Could he hold it and keep it from moving backwards? What do you think? You say no? Okay, all right, so you're saying no, and I'm going to ask Drew, what is your bench press? 185. Okay, so we'll go to 185, okay? All right? So if he can give more than 85 or 185 pounds of force, we'll say that he could make that happen. Okay. All right. So let's check it out. How do we do that? Well, I'm going to make a vector, And here's what I have. And this is where the drawing gets confusing for people. Okay, that 3,200 pounds, that's measured as weight, right? And that's perpendicular to the surface of the ground, right? So forget about the incline of the driveway, perpendicular to the Earth's surface. So we will say that this is 3,200 right there. That's that force vector. Okay. Then there's other forces that we can draw here. There's the vertical component, and there is the horizontal component. Okay? And notice how that vertical and horizontal component form what kind of an angle? 90-degree angle? Good. So which color am I trying to figure out here if I want to try to figure out the force from keeping it from rolling down the driveway? Which one of these represents going down the driveway? The red, the blue, or the purple? The purple. The purple is on its way down the driveway. Yep. So I want to figure out this purple here. Well, that's not that big of a deal. I have this here. I just need an angle. If this is 12 degrees and this bottom part here is obviously 90, can somebody tell me what this would be up here? Not about 78, actually exactly 78 degrees. So can you now see my triangle I've constructed? So 78 degrees, does the purple represent the horizontal or the vertical?
Horizontal.
Which is it?
Ask somebody else.
All right, how about this? Whitney will help you connect here. Okay, you ready? Watch. Okay, everybody, look at this. Everybody agree that 3,200 is the hypotenuse? Is the purple side the opposite or the adjacent? Adjacent. So what has to do with adjacent and hypotenuse? Cosine. So I can tell I'm using cosine, so that's the horizontal component. So I'm going to set up the horizontal component is 3,200, okay, times the cosine of 78 degrees. And we said that we need to come up with a number less than 185 if Drew is going to not get smushed by this. So 3,200 times the cosine of 78, and I get, oh, sorry, buddy, not making it. Now, what I just spoke isn't 100% accurate, okay? Wendy, would you stand up, please? So try to get my point here. No, you're going to try to open the door. When I point at you, try to open it, okay? So I wasn't pressing it all with my hands, was I? So just using, my foot kind of as a wedge, I was able to definitely apply enough force to keep that. So the truth is that maybe Drew could do it. Maybe he could just put his foot or his, I don't know, his shoulder, arm, something underneath the tire. Maybe that would provide enough. Okay. All right, good job. Last example. Here we go. Last one of the unit. You're going to back up to number 9.
The jet problem.
4 people watching.
We're going to change it up. I don't want this to be too confusing. So we're going to say a pilot is headed in a jet north 80 degrees east at a speed of 450 miles per hour. And then the wind's blowing at a speed of 60 miles per hour. And, you know, we kind of want to get an idea here of how fast the plane is really going. I'm guessing that you guys have noticed, as you guys have driven for a little while, that when you have a tailwind to your car, that you get better gas mileage, don't you? Yeah, you do, because it requires less work and less effort to drive when you have that tailwind. But if you're headed straight into the wind, then all of a sudden gas mileage gets reduced. And same thing that happens with planes. So anybody take a flight recently in the past? I mean, kind of a bad time, you know, be asking this question because there haven't been a lot of flights lately. But how about this? Has anybody watched somebody coming in on a flight? There's like that time estimator.
Yeah.
Yeah, and how do they figure that out when you take in consideration the speed of the plane as well as the wind and everything else? And that's what we're going to lay out right here, okay? And so I'm going to draw this example. We're going to use this space right here. And the first part I'm going to draw is that the plane is headed north 80 degrees to the east. Do you remember how to draw north 80 degrees to the east? Now we're going to turn 80 degrees towards the east, so it's going to be going at that angle, approximately. So what angle does that leave me with against the x-axis here? Everybody okay with 10 degrees? All right, so I've got a 10-degree angle there. So that's represented by the jet, and the jet is flying how fast? 450. Good. And then we have this other piece where the wind is blowing as well, okay? And the wind is blowing, and it's blowing at a speed of 60 miles an hour, but north 20 degrees east. So I'll draw it about like that. And that would be a 60 miles an hour. So I'm going to draw it shorter because it's only 60. It's not 450. And then what angle would be formed against the x-axis there? If it's north 20 degrees east, what angle is formed against the, yeah, 70. We got 70 there, good. Okay. So 20 degrees to the east, and it's a total of 90, so 70 is left over. Okay? So it says express the velocity of the wind as a vector in component form. So all I want to do, it sets it up for us in nice 4 steps. And we're going to call that A and that B. So we want the vector expressed in component form. So I have A, B. How is it again that I find A? $60 times cosine of 70, and the B would be 60 times sine of 70. That's the most complicated part of this problem, I think. Okay? Really, the rest is quite simple. You good with that? Okay, so let's do that. And I've got 60 cosine of 70. And I get 20.52. And then I've got 60 sine of 70. And I got 56.38. So that vector in component form is 20.52 and 56.38. And this helps us get a little bit of perspective here, okay? It tells us how much that wind is helping horizontally and how much that wind is helping vertically, okay? So it's not just a really great tailwind, but it is helping it, isn't it? Yeah. The question is kind of how much, and that's what we're going to be figuring out. It says express the velocity of the jet relative to the air as a vector in component form. So we're going to do the same thing, but we're going to do it for the jet now. So the jet has a horizontal component, and it has a vertical component as well. How am I going to figure out that horizontal component? 450 times the cosine of what? 10. And then B would be 450 times the sine of 10. So I'll come up with those. And I get 450 cosine of 10, 443.16. And then I've got 450 times the sine of 10. and I get 78.14. So those are my two vectors. Obviously, this one is having much more of an impact horizontally, right? A little bit vertically. But the wind, definitely some horizontal, more vertical. We're going to see how much they do together. So it says, find the true velocity of the jet. Velocity, all we do is we just add the two together. So we're going to add those two vectors together. And I have 443.16 plus 20.52. I get 463.68. And then I have 78.14 plus 56.38. And I get 134.52. So what I want you to do is I want you to look at both of these. Look at the jet here, and then look at the jet there. This is the representation of the jet with the wind. Would you agree that the jet's probably going faster with the wind than without the wind if you look at the numbers? Good. In order to relate it to you to understand better, what we're going to do is this last piece, which is find the true speed. Does anybody know how speed and velocity compare? Speed is simply the absolute value of velocity. Or in other words, the magnitude of the vector. Does anybody remember how we find the magnitude of that vector? Yeah. So you take square root of 463.68 squared added to 134.52 squared. So I'm going to go to my calculator, and I'm going to do 463.68 squared plus 134.52 squared. And I will square root that answer, and I get 482.80. Now, how fast did we say the jet was going originally in miles per hour? 450. It ain't going 450, is it? It's actually, with that wind, it's actually going 482. Is that going to change our time of arrival and everything else? Yeah, but here's another thing. They also need to impact that wind is probably going to blow it off course a little bit, isn't it? So the last thing we're going to do is find the direction. Do you remember the formula we used to find direction of something? We've done it 50 times so far in the past 5 days. Hint, starts with a T. Tangent of theta is equal to, yep, so 134.52 divided by 463.68. And you know how to solve that, right? What do we do to solve that? Yep, we just do the inverse. Who cares about the big numbers? Tangent inverse of 134.52 divided by 463.68. And I get 16.18 degrees. So look at the plane. It was flying at a 10-degree angle. Is it really flying at a 10-degree angle? No, it's flying at a 16-degree angle there. So in other words, if this was a 16.18 degree angle, that means its direction would be north 73.82 degrees to the east. Somebody tell me how I came up with 73.82 degrees to the east? Subtract it from 90. Congratulations, you made it through that unit. You made it through the jet problem. Jet problem is a tough one.